So today I thought I'd make a quick video discussing some wave shaping techniques and my approach to reverse engineering, particularly today with distortions and static wave shapers. So I wanted to outline some of my techniques for that, and then a little bit of the theory, just so that people understand it better. I know there's some requests to cover some of this before, so just throwing it together now. So a few weeks ago, I reverse engineered the Kush Omega N with a Max for Live Vision. I actually really like this company, Gregory Scott, and he has a good podcast. He makes, I think, good hardware and software, although I don't have any of the hardware. I don't really like iLok, so I wanted native version running in Ableton, and I thought it would be a good project to try to recreate it in Max. Good exercise to try and see what's going on. One other motivation, I guess, is sort of the just some of the marketing. I don't think Kush is the worst defender for this. I read this blurb here about the Dusty Patina and just the kiss it imparts. So it's pretty funny. Some plugin marketing can be a little bit misleading and maybe even predatory. So I think it's important to keep grounded and understand what's actually going on behind the scenes. And one of the motivations, I guess, is that I think a lot of people probably already have something that does exactly this in their native toolchain, and it's just they maybe don't know they don't know about it, or maybe it's the convenience of having a drop in place plugin. Certainly something I value, but I think it's good to learn these things. So I'm going to jump in with some basics on wave shaping first. So I've got a graphing calculator, have Desmos open. So if I do y equals x, don't get too scared of the math here, and we zoom in. So if we look in this square, basically this is an amplitude map. So the input amplitude would be the x-axis going from -1 to 1. So your standard amplitude values generally are within that range for digital audio. And your output is the y-axis. So let's say the input amplitude for a given sample is -0.5. So that would be this point here. And then you see where it falls on this map line. And you can see it's mapping to -0.5, which you can kind of read right here anyways on the y coordinate. So let's try another one. Let's say 0.8, positive 0.8. So in this case, we already know it's just mapping linearly. So what happens when the mapping is not linear? It's not one-to-one like this. Well, that's where you start to get some distortion. So to see this better, let's just set up a x1 function as our input. And what I like to do is have maybe a mode, let's call it m variable, and have two conditions to make a piecewise function. So when m1 equals 0, x1 equals x. And we can see we need to add the m1 slider. And when mode equals 1, x1 equals sine pi x. I do sine pi x usually because then we get one cycle from 0 or from -1 to 1, so it just scales it correctly. And we could just make this just go between 0 and 1 in one step. So now you can see we're switching between y equals x to y equals sine pi x. just as our input function. And we can close this because we don't need to see it. So what happens if instead of y equals x, which is linear, y equals the hyperbolic tangent of x? We'll do x1 to use our input function. So that's what tan h looks like. So you can see at -1, which is where this is bounded, sorry, here, our output amplitude is only -0.7, and this is symmetric, so it's the same over here. So what it means is the input is, or the output will always be between -1 and 1, and when x is just x times 1, I guess, there's no amplitude or no amplification, then it's actually reducing the level of that sample as you're approaching the extremes, -1 and 1. So actually this is compression, it's not time variant compression, but it's also distorting. Also, as you figure some of this stuff out, you'll realize compression is also distorting. So it's sort of the two go hand in hand. Usually people talk about compression, and it's like a time variant compression where you have an attack and release and threshold and knee. But this is also a type of compression. So it's worth adding another variable here, which is a gain slider. So right now we'll go from, say, 0 to 20, and we won't put a step amount. So what we see is, as we're scaling, this is inside the tan h function. So we're multiplying x by a gain, and then applying the tan h function. So you can see it gets a lot sharper. I should also note when it is equal 1, when it's unity gain, most of the tan h function, the first almost half of it, matches just a linear function pretty closely, which is very handy. So at unity gain, you might call this section sort of like a small signal response. So it's quite linear. Where it diverges on the ends here, you'd say that's maybe the large signal area where it becomes non-linear. And that's very useful for modeling analog circuits. So we see what happens to tan h when we increase the gain. Now what happens to a sine wave when we put it through? Well, it starts to square off. So if you look up the Fourier series for a square wave, which gives you a harmonic analysis, so you're adding sinusoidal components, or you're decomposing it into sine waves. You can recreate a square wave with a sum of sines like this, and the more you have, the more detail it gets and sharpness it gets and everything. But the thing about this function is that it's only adding odd order harmonics. If you take a look at this summation here. So this response here, just a square wave, is only going to produce odd order harmonics. The other way to make sort of an eyeball judgment of this is by putting in a y equals x line, and it will be odd symmetrical if anything on this side it would be the same as what's mirrored over here, which you can see is the case. So let's take a value, maybe, what's an easy one? Maybe just the point right here. X equals 0.5. Well, at -0.5 you can see the y values are just inversed. And the same goes along any point here, so it is odd symmetrical. An even symmetrical function would be if it's mirrored along the x equals 0, the vertical axis, which you can see is not the case. An example of this would be like sine pi x. So our normal sine, But if we absolute value it, so we're taking only the positive values and then flipping the negative portion, then you can see along this axis it's the same on either side. Now we also only have the positive signal, so you'd have to remove the DC offset, the bias, but this would produce even order harmonics. So I think it's pretty intuitive how this wave shaping function works, and you can see again, this is our function, this is how it's mapping a sine wave. You don't really have to understand the math behind hyperbolic tangents. That actually gets a little bit more complicated, but I think you can kind of hopefully visualize the mapping, the amplitude mapping, which is the concept I'm trying to get across here. So let's take a look at reverse engineering plugins such as Omega N and go through the process. So this is my typical sort of test bench setup. I have a signal generator, Max for Live device, where I can choose different sine waves, different amplitudes as well. Then I usually have a grouped audio effect folder with the plugins I want to test, and then followed up by a spectrogram and an oscilloscope. Lately I've been using the Melda oscilloscope, which is free, very quite responsive and stable oscilloscope as well, so I do like to use this one. And then in my folder here I have a couple wave shaping plugins. This is my own Max for Live device, where I have 10H and then a few other equations as well as hard clipping, so it's nice to try a few. And then it has my common parameters, bias, drive, mix, those kinds of things which are important, and also the plot. The Melda Waveshaper, you can draw a symmetric, or the asymmetric view would actually give you what we were looking at before. We have the negative quadrant and positive quadrant, and you can basically just draw whatever shape you want with splines, and then there's some different interpolation. And the new one, I'm just trying this out because it's in beta, but I have a lot of respect for Chow DSP, and his new plugin has this wave shaper with a bunch of modes, 10H, cubic, rectification, West Coast is probably a sine, but then you can also draw your own, and then you can see by the edges here it's band limited, or you can type in an equation, which is very nice. So 10H populated right away. I could do sine x. So that's very handy. Or you also have a spline mode. I find this one is maybe not quite as intuitive as the Melda one, because you have to sort of click them in the right order, and yeah, it's a little trickier to navigate this one, but I really like this this math function, just being able to type in your own wave shaper. So highly encourage people to check this out, and even if you're just sticking to the stock ones, I think this could replace like FreeClip or any plugin like that, the stock Ableton saturator. Alright, so we have Omega N opened up here, and we can turn on our signal generator. I just added a gain to turn down the output a little bit so it's not too annoying, hopefully. So you can see we have a sine wave where we just have the Omega N soloed, and when the processing is right down, it's pretty much passing a sine. You can see there's a few harmonics being added already, but it's pretty minimal. So If we start turning up the intensity, I'll just turn up the gain a little bit. We can see this harmonic structure. I think this is an important thing to look at, and this is just one of those things where you have to sort of get familiar with it, and then you'll start to recognize it. So first of all, I'm using 100 hertz because it's easy to count multiples of 100 on the spectrogram. So you see we have our fundamental frequency at 100 hertz here, and when the plugin's bypassed and we have a sine, that's all we have, is just the 100 hertz. Now we have this harmonic structure, and you can see over here the frequencies of each. So 300, 500, 700, etc. So this is all the odd harmonics. So that's the first thing to notice here. We have only odd harmonics, no even harmonics. The second thing to notice is just this harmonic distribution sort of falls off quickly like this. Now this is also the spectrogram is a log plot, not a linear plot. We can change it. If you want to see it in linear, we can do that on spectrogram, and then it's sort of a straight line. But we usually look at log plots because they're more relevant to how we perceive frequency. So one thing I recognize with this harmonic distribution falling off like this is that it really corresponds to tan H. So if you want to see what tan H looks like again, we can move over to B314, named after a clipper because it is a clipper, and mix it 100%. We see pretty much the same pattern as we increase the gain. If we compare that to some other algorithms, such as this one's linear over the log plot. I've heard this one called asymptotic limiting, but I think it just goes by a few names. It's just a absolute value expression. And in the linear plot, it looks even crazier. And you can see there's some aliasing down here as well as it's folding back. One nice thing about tan H is the roll-off of the frequency response is quite controlled, and I think quite natural sounding. It's not quite as bright, but you kind of know it's going to be, if you look down here, well, we're at like negative 168 decibels, so that's well below the noise floor. We don't care about anything down there, so we can apply some gain. I still use oversampling because, say you have, instead of 100 hertz, you have 5 kilohertz. You can see if you have any sort of high amplitude, high frequency component, you're going to get aliasing. I think this is with 4 times oversampling as well, but you can see the peaks folding out again. Even without oversampling, tan H is pretty well controlled compared to some other wave shaping algorithms. So let's go back to omega n. The next thing I would do is take a look at the oscilloscope here. With it right down, we're seeing just our unadulterated, more or less, pure sine wave. And then as we turn this intensity control up, it starts to flatten out. But one thing I'm noticing is that it sort of has these bulges at the corners, or sorry, at the peaks. It's not as flat as you'd expect. And as we continue on, you might sort of notice it's almost like there's 2 overlapping waves, like the superposition of 2 waves, one that's sort of flat and one that's more rounded. I know it's a little hard to visualize, and this just comes with experimentation and familiarity. So don't worry if you can't see it right away, but that's just sort of what I notice when I'm looking at this. So, well, what could that be? in signals, the simple answer is it's probably two waves that are being mixed together. So, how would we go about doing this? We have sort of a flattening of the wave as it's getting crushed, and it sort of turns into a square. I can also on this plot you can visualize it. Um, so, what happens when I mix the dry signal in? Well, you start to see this shape. Um, so this is the dry signal, 100% dry, 100% wet, and this bulge, well, that's looking kind of familiar to me. Now this is a lower level, which is why I said I think the intensity knob is not just performing input gain, it's controlling the gain, the input gain of the distorted signal, and um, I think either controlling the mix a little bit as well, or just scaling the output gain. Um, but I think that's an easy thing to do manually, or you could even set it up with some macros or something if you want. Uh, but say you have a plugin like this, any sort of saturation plugin with a mix. I think even the Ableton saturator would do this. This is probably 10H in the Ableton saturator. So what if you mix in? Well, you're getting kind of the same thing in saturator. I don't know about other DAWs. I'm pretty sure a lot of them have a very similar Waveshaper with a mix control. Yeah, it's just a very simple effect. So I think if you're interested in learning this, it's worth just using the tools you have instead of buying a different saturation plugin such as 10H over and over and over again. There's free ones out there like my Max for Live device, like Free Clip, Mellow Waveshaper, the Chow DSP one, and just using the tools you have if you're interested in learning the concepts. Now, if we want to go a little bit further, so I actually set up this other Desmos graph that walks you through sort of the process like we talked about here. We have this is with the amp control. So those are the input functions. Here's 10H, 10H with the sine, and again you can see it working on both functions. And now if we put together the dry signal, which is a sine wave, with the saturated, the squarified 10H signal, we can see this function, and when we turn up the mix, we're adding them together, and then of course controlling how squared the square signal is. Now this is going above 1. I actually think on the Kush one, the mix percent, it's like 4% or something. It's very small, so like 0.05, let's say, is probably the mix. So the amplitude is pretty tame, and you could even knock this down on the dry signal a bit. Just to scale it down. So then, yeah, you can see we're getting that shape. So there's one more concept that's worth exploring for this, which is the amplifier classes. So class A, we're just biasing the bass. You don't have to worry too much about any of this, but what it means is the output is like, it's never actually swinging down to 0. It's like swinging between the bias voltage, which is this line, and then like above and below that, but never all the way down to 0. So this is a very clean amplifier in a sense, as long as you're within the sort of small signal linear range of the transistor. Uh, but there's other classes of amplifiers, such as class B, where you actually have two sets of transistors. Um, it's called push-pull configuration, and this top transistor is amplifying the top half of the wave, and the bottom transistor is amplifying the negative cycle, and then they're being added together. But this leads to crossover distortion. We can look at some simulations. This is our class A common emitter amplifier, where we're just reading here, and the I know this is a Java application, and the integration is a little bit choppy, um, but you can see it's a sort of a nice clean sine wave. Here's a class B. Um, so we're reading the signal here, and I'm gonna zoom in a little bit. So this section right here is the crossover distortion, and it's because there's actually um, a junction voltage drop between the base and emitter here and the base and emitter here. If it's silicon, this is going to be about 0.7 volts. For a germanium transistor, I think it's 0.4. We can actually measure this and see what the simulation's coming up with. Yeah, so about 0.7 volts on each one of those. So that means there's a time when both the transistors are off, neither one is amplifying, which is why we get that effect. So it is sort of a naive amplifier design, although with some resistors you can kind of make it work. Then there's a type of amplifier that improves on this, called a class AB amplifier. So here you have two diodes. Now they have approximately the same voltage drop as this transistor junction, so it sort of compensates for that, and you can see the distortion on the output is basically gone away. While it's technically a flaw, you might want to model class B crossover distortion. And so if you were to model that with a Waveshaper, what would it look like? So you can see we're linear, and then as we add this tan term, you get this little hump, right? And now we can control the mix of the dry term. So what does this do to a sine wave? This is the straight input, and then the amplifier output as we're adding that distortion. You can see this sort of crossover. Now this is the exact same equation we were using before. One other thing we could play around with is, I'm just going to change the mode back to linear. So what if we have a negative gain on the tan H term? So then we get this sort of flat section. So you actually might see two types of crossover distortion, or there's two ways to model it. This would actually be what that class B amplifier was doing, where it's going to zero a little prematurely, and it's sort of lingering at zero on either side of the peak. So I think that's sort of what we were seeing before, and you can control the amount of it very easily, or we could go the other way and control it here. So what's the takeaway? If we really look at this configuration here is basically what we had in the omega n. So my assessment of it is basically a type of crossover distortion that they're modeling. I'm not sure if that's the most accurate way to model a naive circuit, but I think the plugin sounds good, and knowing that we can easily emulate it. We have our clipper plugin. You can see that shape here. What if we want to get the other type of crossover distortion? We need negative gain here. Well, just because I wanted to scale the knob exponentially on this plugin, you can see like this is 0 and we have a lot of granular control for lower values and then much less here. So I decided rather than a bipolar knob that goes from 0 to negative 100 or 0 to 100%, I just include a inverse polarity button here. So now we're getting the other type of crossover distortion. I think a little bit goes a long ways with this, so you can do both with this plugin. That's one version of crossover distortion. We can see the same sort of effect. It's we have some even order harmonics because this isn't perfectly symmetrical. And then this would be the other kind. So you can see on this website there's an explanation of crossover distortion, and you see that same shape we just created that gives you this, or this shape that gives us that. So there's one more pretty fundamental concept, and I think it's actually better to demonstrate with Omega Tweak, which I also sort of did some basic reverse engineering on. So actually at first I thought this was just a hyperbolic tangent with nothing else. Like that's sort of the shape you see, what it looks like. It's just squaring the wave, has that harmonic fallout. I'm just gonna turn on the audio for a second. So it sort of sounds like a 10H, and it has the similar harmonic distribution where it falls off quickly. But there's one crucial difference that I missed at the beginning, which is these other harmonics here. So we look at our frequencies. Our fundamental is 100. We have 300 hertz about where we'd expect it for a 10H, but we have this lower level of 200 hertz and then 400 hertz and 600. So we actually have a spectrum of even order harmonics as well. So how do we get those? Here we have our sinusoid going from -1 to +1, as we'd expect. But in math, you can just add some offset to this, which is literally just adding or subtracting a constant number. In electronics, it's the same thing. You'd add a DC voltage to the AC signal, which is how those transistors and tubes are biased in the first place. So this is an important concept. So what happens when we add it in here? You can see we're actually coming up against the headroom the more we skew the wave up or down, because that 10H function is like clamping to -1 or +1. It's never going to go above those extreme values. So we're sort of weighting it more positive or more negative, and coming up against that headroom. This is also how a transistor would work to some extent. You get out of the linear range and it starts to fall apart pretty quickly. So let's do the same thing in our Clipper plugin and add a little bit of bias, which conveniently there's a knob for that. And yeah, look at that. And we get a very familiar harmonic structure with these. We can kind of control the level of these even order harmonics to some extent with the bias. And yeah, it looks a lot like the shape of the Omega Tweak. So just with this one Clipper plugin, we can kind of model both Omega Tweak and Omega N pretty accurately, and we can take a quick listen to them as well. We've been mostly just looking at the waves, but we can hear sort of the final result here for the tweaker comparison. So this is tweaker. Sounds pretty similar to me. And now omega n. So the clipper. And I actually made a Max for Live device that's just basically the same controls as this without the extra features of B314. So we can check that out as well. Thanks for watching. I hope you learned something. If you're interested, if you're an Ableton Live Suite user and you'd like the Max for Live devices, there's B314 here, Trans N, which is the Omega N clone, a bunch of other devices. They're all free donationware, so costs you nothing to get these. But if you're not an Ableton Live Suite user, I know that's a little bit niche, but basically any clipping plugin with a mix knob can do this, preferably with 10H, but most of them will have 10H even if it's not called that.